So we've looked at some definitions for the different things we're going to be talking about in communication. Now let's look at the rules for how we set up this type of communication. The most basic type of channel of communication is just a blinking light. So this hello world that we've been building all semester over and over again, as we control the timing of it, we can actually communicate information. And here's a neat trick, is the camera on your phone, or if you have a digital camera, is sensitive to infrared light. And if you shine the remote control for your TV into into your phone, or look at it with a camera or anything like that, you should actually be able to see it turning on and off. Now, what is that? What do these blinks mean? How do we communicate information with just these pulses of light? Enter the protocol. A protocol is a set of rules that allow us to define a communication between two endpoints in a network. And a network can be something as simple as the remote control of your television and the television itself. Often these protocols have components that define the standards for communicating information, including what does a 0-bit look like? What does a 1-bit look like? How do we start and end a byte, and how our message is formatted in larger and larger sizes. And these protocols can be defined at a lot of very different levels. This is the OSI Communication Model, and it starts down here at the bottom, defining a bit. What are the physical characteristics of a bit? How do we represent a bit? In electrical protocol, it might be voltages that define a bit, or even voltages and timings. For an optical protocol, is how long is the pulse? What is the optics? What does the optical range look like? Things like that. Then a frame is the definition of how does a message start and stop. How many bits are in a message? How do we define the boundaries of a message? And packets and datagrams include things like addresses and where the message should be delivered and stuff like that. So you can see we're adding layers of detail to our protocol as we go up the OSI communication model until we get to application, where we are developing some kind of network application. It's the device itself, or the software itself, that is communicating back and forth with the underlying physical network that we've developed. So let's develop a protocol for the this infrared remote control. And the first question I need to ask is, how do we represent a bit? I don't want. You might think just like, oh, it's on. If it's on, then that's a 1. If it's off, it's a 0. But if the remote isn't sending anything, then I don't want it to receive a whole string of zeros. That might be a valid message. So we're going to define our bits as different lengths of pulses of light. So a 0 will be a short pulse, and a 1 will be a long pulse. Now the next question is, how do we define a frame? How do we define the start and stop parts of a message? So if we've already got 0 and 1 represented, I kind of need a third symbol to define when a message starts, right? Something that's unique, that says that it is a new message, it is a communication that has begun, and we want to know that this is not a normal bit. So we'll make an extra long pulse as our start bit, and if there are no pulses, then that's stop. That means there's nothing that's happening, right? And then finally, part of the standard of how messages are formatted are how are these bits sent? What order? Is it going to be the most significant bit first, or is it going to be the least significant bit first? This is more like the bit pattern rather than the byte pattern of endianness. And in our standard, we're just going to set it as most significant bit first, because it's a little easier to read this way. And we'll talk about how this works later. So here's a flowchart for our protocol, and you can see we start in the idle states, right? So whenever we're in the idle state, this is where we're just waiting for a new message. And in this state, the only thing we're looking for is for the start pulse to be received. So we're waiting, and if we receive a long duration pulse, then that takes us to the receive message state, and we're now waiting for a 1 or a 0, one of the medium length pulses, or a short pulse. If I get a long pulse received, then I'm going to take that as a 1 and shift it into my receive register, increment my bit count, If I haven't seen a whole frame yet, then I'm going to go back to the receive message state. If I receive a short pulse, I'll take that as a 0, add that to my receive register, increment my bit count, and I keep repeating this cycle of long and short pulses until I get an entire byte, which in that case should take me back to the idle state. So let's look at how a communication with this might actually work. So we'll start off with our signal over here. We're in the idle state, and the signal is idle too. So we're receiving all stops where there's nothing there. I've also got my receive register. I'm receiving 8 bits, so I'm waiting for those to be filled in, and I'm keeping track of my bit count. So we start out in the idle state. And the first thing that happens is we should receive a start pulse. We have a function that is timing how long a pulse is, and it gives us that this is one of the long pulses, and we're going to mark that with an S, which takes us to the receive message state. Now we're waiting for a new pulse to come in. It turns out that this new pulse that comes in is the long type of pulse, so we're going to mark that one as a 1, and we're shifting it in from the right. So we're shifting in from the right, which means that as we go, this 1 is going to march over, so this is the most significant bit that we've received so far, and that one gets pushed in first. And the next one that follows it is going to get pushed in until the first bit that we received is in the most significant bit position. After we've shifted in our 1 bit, we increment our bit count. Then bit count is less than 8, so we're going to go back to the receive message state. Now, the next bit that we receive is a short pulse, so that we identify that as a 0. We shift a 0 into our receive register, increment the bit count again. Then we know that it's still less than 8, so we go back to receive message. And we keep going through this, receiving a 0, receiving a 1, receiving a 0, a 1, a 1, and we keep shifting in these things until we get 8 total bits. And now once that's happened, we have received an entire byte, and the current position, the current data inside the receive register is valid, and we can go back to the idle position. Right? So this is an example of we've received an entire frame starting with a start bit, a series of 8 bits, and stopping with the stop long 0 idle condition, and this is how we can identify the information that's being transmitted over a communication channel using a protocol to decipher what each of these pieces mean.